Good afternoon. Today is Good Friday, and today is also Bengali New Year. So, Subha Navavarsa to all Bengalis. And also,
Thanks, Muna.
okay. So, actually, last lecture actually was embarrassing for me because I lost my connection abruptly, and I hope you will not mind it. But okay, so what you are discussing last lecture actually something like that. If G is not pseudo-algebraic, then also we have an polar decomposition. We can get also polar decomposition for that group, and we have to. There are two important examples, something like GLN plus R, and this is SO naught P comma Q. Okay, so last lecture we have proof ended with something like SO naught comma P comma Q is a does U plus P U P plus Q. This is something like SOP cross SOQ. Okay, so from there you can get this phi1 of SO naught P comma Q is something like phi1 of SOP cross phi1 of SOQ. This is a very important thing. We will later actually use this thing. So now today we will discuss something called pseudo-unitary group. So this is denoted by U P comma Q. Pseudo-unitary group of signature P comma Q, P greater than 0 and Q greater than 0. Today you will, this is really an automorphism group preserving some Hermitian form, not bilinear form. Last time I also gave the definition of Hermitian form. It has exactly the same properties of inner product except the positiveness. Okay, so now just wait 1 second. Okay, so let Z belongs to C P plus Q and W belongs to C plus P plus Q. Okay, so I define this is some H Z comma W. This is equal to I is equal to 1 to P Z I bar Wi minus I is equal to P plus 1 to P plus Q. This is Z I bar Wi. Okay, so and okay, so this is a really H is a this is a non-degenerate Hermitian form. Hermitian form. Okay. Now and let U1 E2 EP plus Q be the standard basis. So analogous to the theory of bilinear form, actually we can really associate a matrix to this Hermitian form, and we also form the automorphism group. Okay, so here this associated matrix is IP comma Q with respect to the standard basis. So now this UP comma Q, this is A belongs to MP plus QC, so that H AZ W is equal to H ZW for all Z comma W belongs to CP plus Q. So this is same thing as I have, you know, that this is H of AEI. A is A for all 1 less than equal to I comma J less than. Okay, so now you can get this A belongs to MP plus Q. See, so here this would be A star I P comma Q. A is equal to I P comma Q. In the bilinear form, we get A transpose, but here you get A star. So this you can same thing as this is a subgroup of GLP plus QC. So you can write this GLP plus QC. Now, so SU P comma Q define, this is the definition. This is A belongs to U P comma Q. So the determinant of A is 1. Clearly from the definition, this UP comma Q and SUP comma Q are pseudo-unitary. So clearly UP comma Q and SUP comma Q are pseudo-unitary. So UP comma 0, U0 Q, these are nothing but unitary matrices.
Muna, I have a quick question.
Yeah.
So
yeah.
Whatever pseudo-algebraic group we have seen so far, I think the coefficients of the polynomial by which they are defined, they are real, right?
No. That may be complex. Actually, you asked this question itself. They may be there will be they may be complex.
No, I'm not saying that. Before this, whatever you are doing today, before that, whatever you have done, whatever pseudo-algebraic group you have taken,
yes,
those coefficients are real, right?
ONC, what about that? I think ONC, yeah, real, yeah. Okay. Yes, real. Then?
But is it the case for this group?
I think it will not be. Just wait. Okay. A star. That may be real or complex, but it doesn't. Why does it bother to you, right?
No, just a curious question.
Yeah. I have to think. Actually, I can see that these are real, but the thing is, I have to make sure before I am says some mathematical statement. I have to very sure about it.
Okay, just think about it. So
just now.
No.
Yeah, tomorrow I will. Next lecture I will say it.
Yeah. Okay. Thank you.
So this is UP comma 0 and U0 comma Q are unitary matrices. Just wait. I will take some water. Just wait. Yes. So now onwards we will assume. We'll assume P greater than equal to 1 and Q greater than 1 onwards. So now the thing is observe that okay, OP comma Q is contained inside UP comma Q, because if a matrix A belongs to OP comma Q, then that will be real matrix. Then A transpose is equal to S transpose. So therefore it will clearly satisfy this equation, this thing. Okay, because A star is equal to A transpose, and A transpose IP comma Q is equal to IP comma Q by definition. So you get that OPQ comma Q is contained inside this thing, and this SOP comma Q is contained inside SUP comma Q. And this is, now you know that this thing is unbounded. So that means this implies SU P comma Q and U P comma Q are non-compact. So now for connectedness, I have to first prove that plane so A belongs to UP comma Q. This implies A star belongs to UP comma Q. So that means let A belongs to UP comma Q. That will imply that A star IP comma Q A is equal to IP comma Q, and you apply the same argument. You multiply IP comma Q on the both sides. So I will get IP comma Q square, and IP comma square is the identity. Now we have also seen that if C T belongs to same NC, CD is equal to I identity. This implies DC is equal to identity. So for me, this is B C, this will be D. So then that will give you IP comma QA and IP comma Q A star is equal to identity. Now you multiply IP comma Q in both sides. So IP comma Q square A P comma Q A star equal to IP comma Q. Now IP square Q square, this is identity. So use that. So this will be A IP comma Q A star equal to IP comma Q, and this A star star IP comma Q. So this implies A star belongs to UP comma Q. This is the same argument which we have given similarly. Okay. So since determinant of A star is equal to determinant of A bar, it is also clear that A belongs to so this is the thing. Now you can apply that polar decomposition theorem which we have proved for pseudo algebra group, and for that we need to really find this its intersection with UP plus comma Q proposition. First proposition is UP comma Q. This is UP plus Q. That it is very easy to actually guess this thing if you are you've done this because we have done this for OP comma Q. If you guess this will be something like UP cross UQ, and that will be A 0 0 B, so that A belongs to UP and B belongs to UQ. And second thing, Pratham, can you guess the second thing? SUP comma Q intersection UP plus Q. Okay, this will be S of UP cross UQ. Okay, so this will be A 0 0 B. So that A belongs to UP, B belongs to UQ. This is equal to 1. Okay. So, Pratham, are you there? Hello? Is anybody there?
Yes, I can hear you.
Okay. Okay. I thought that. Okay, sorry. Okay, this will be the thing. Proposition. Actually, proof is really exactly the similar to the case of this OP comma Q. Actually, I have written the proof in a way that you have to only change a little bit of symbols and exactly same argument will work. So proof first. I will not do the proof actually. So examine the proof in OPQ case and modify appropriately. You have to just change certain symbol, that's all. Actually, I have, for that reason, actually, for example, you have to, for instance, you have to change this RP, change to this, to CP, RQ, into CQ, and UOP plus Q to this is UP comma Q, something like that. This is OP plus Q, you have to change to UP plus Q, and this inner product with RP, you have to change that CP like that. So I have actually done that thing, and you can do that. Actually, I will not do it. So second thing is also similar to that, similar to SOP comma Q case. Okay. So now the thing is from here actually it is easy to see that this is connected. So this UP comma Q will be connected. So that is so corollary. Let me write it as corollary. So applying previous proposition and polar decomposition theorem. We get that you see that as UP comma Q is connected. So this is, but however, this is not clear from this moment that whether what about this group? It is not really clear that whether this is connected or not. We will see that this group is connected, but we have to do some work. Okay? So we will do it, but now we have to little. So let us little bit digression or discussion, slight digression. So let us discuss this thing. Then we will. So you know that SUN is a normal sum group of UN. Okay, so what is the reason for if G belongs to UN and A belongs to SUN? So determinant of this G inverse is same thing as determinant of A, and this is 1. So this implies G inverse belongs to. So
Kernel of a homomorphism should be a homomorphism.
hello, sir.
Kernel of a group homomorphism has to be a
homomorphism. Yes. Actually, you can so that this SUN is a kernel of the homomorphic determinant. For that reason, it is also normal. Okay. So this is also okay. So will I write this? Okay. Since this is SUN is the kernel of determinant map, Therefore, it is also null. So this is another way of saying that. Okay, it is okay. So now, so S1 actually S1 sits as a subgroup of UN. So S1 is really diagonal of e to the power I theta. This is 1, 1, 1. Okay, so theta belongs to R. This is a subgroup of UN. Okay. Now let us let G belongs to S1 intersection UN, SUN. IS1 means this subgroup. Okay, this is the thing by S1. Okay, so that implies since G belongs to S1, so G is equal to so diagonal of e to the power I theta 1, 1, 1. Okay, so now since G is S1, I will put determinant of G both sides. Okay, so this will be e to the power I theta. Okay, but G belongs to SUN, so this is equal to 1. Okay, since G belongs to SUN. So that means e to the power I theta is equal to 1. So that implies G is equal to identity. So what I get is S1 intersection SUN is equal to identity. Okay. So now, so let A belongs to UN. Okay. So that means A is some matrix Aij. Say, okay. Now I write A in the product of two elements, one element from S1 and one related from S1. A you can write like this. First you put determinant of A here and the rest of the diagonal elements as 1. Okay, and first you divide by this first row by determinant of A simply. Okay, so determinant of A by simply. So and you keep all these rows as it. Sorry, 8 to 1 it should be 8 to n. Okay, so I will call this second thing is by AF. Okay. So AF means the matrix obtained from the matrix A by dividing the first row by determinant of A. Okay. So and this by definition, this first element, so this belongs to really S1. Okay, and second element this belongs to S2. So what I am getting then from this thing, I am getting this UN is really S1 into SUN, but 1 is normal, SUN is normal, and S1 intersection SUN is identity. So this means this is a semi-direct product. Okay. So this is actually a group, a, a topological group isomorphism. Means topology also means they are homeomorphic and group isomorphism, all these in the group isomorphism. In particular, there so in particular it is a homeomorphism. In particular, it is homeomorphism. So what I am getting, so hence, and so we get A going to, this is determinant of A, and A is a homeomorphism from UN onto this one cross SUN. Okay. So UN is SUN. This is homomorphism. So this is an interesting relation. In it also implies that if you can prove that SUN is connected, then UN is also connected. That is that will give you another proof. But that is and you will get that from here pi1 of UN is equal to pi1 of SUN, and this is into Z. Okay. So now we will come back to our case. Okay, so this is a interesting small. This is small result, but it is nice result. So now we want to really come back to our case that whether this is S of UP cross UQ, that is actually connected or not. Okay. So let us see.
What definition of semi-direct product you are using?
Semi-direct product. Actually, definition you want to ask. Actually,
Yeah. I mean, how does one see that this is a semi-direct?
This is semi-direct product.
Definition.
Actually, if this is the condition, if you get this condition, S1 intersection S1 is identity, and this these are two groups so that S1 any element of in UN can be written as something that belongs to S1 and something belongs to SUN, then you can really get this as a semi-direct product. This is a theorem abstract result, but it has its own definition.
But it
Will I
may
write that?
also turn out to be, but it may also turn out to be a direct product.
It will not be
Because
direct
that is
product.
also a semi-direct product. But
Yes.
you were saying that it's a genuine semi-direct product.
Genuine semi-direct. That is a
That
exercise.
does not follow from that previous condition, right?
No, because no, that will not follow actually. Actually, you okay? I can put that exercise also. Exercise.
Don't get into that. All I'm trying to say is that suppose G is a group, H1 and H2 are subgroups, H1 intersection H2 is identity, and every G in G can be written as H1 times H2 uniquely. Then it could be a direct product, but it could also be a semi-direct product. So just from this fact, we cannot say that it's a semi-direct product. It could be a direct product also.
Yes,
but in this case, that is not the case you were saying.
Yes. For semi-direct product, you have to show that at least one group is normal, and there's this if G is written as H1 into H2, say H1 into H2. So H1 intersection H2 also identity you have to do. That also you have to ensure. So what I'm saying is G is written as H1 into H2. Okay, that will not give that this is a direct product or semi-direct product. For semi-direct product, you have to really ensure that H1 H2 is equal to identity and one is normal. And for direct product, you have to ensure that for direct product, what you have to ensure H1 and H2 is equal to identity, and H1 and H2 they will commute with each other. So this is for direct product. Is it clear? Hello, sir.
Yes, for me it's fine.
Yes, sir. So that this UN is S1. Sorry, this is not a direct product. Okay, so this is exercise. Now we come back to our case. So SUP. Okay, so UQ is by definition this is really A00B. A belongs to UP, B belongs to UQ, and determinant of A into determinant of B, this is equal to 1. Okay, so let us use a phrase space. Actually, it will not. So let A0, 0B belongs to SUP cross UQ. Okay. So now that means I will write this A00B in two form. Okay. First, I will write a diagonal matrix. So first I will put determinant of A, and the rest of the element I will put 1 up to pth diagonal entry. Then I will put determinant of B, and then I will put 1 1 1. Okay. This rest of the things are 0. Now I will really put AF 0 BF. Okay. So the thing is, this is really corresponds to the first element. This corresponds to multiplication in the first row, determinant of A, and P plus 1 row, determinant of P. Okay. This is actually, this is nothing but multiplies by determinant of A in first row and determinant of B in P plus 1 row. For that reason, and I have shown that if you multiply determinant row into AF, then you will get A. Okay. And you determine B in the P plus 1 row, you will get B. Okay, so now by definition, this AF, so this by definition, this AF, BF, this belongs to AF belongs to where? SUP, and BF belongs to SUQ. And I have one more condition, since A0 0B is in this is in S of UP plus UQ, so that means determinant of A into determinant of B, this is equal to 1. Okay, so I will put that, use that, so that will, I can write that same thing as determinant of A 1 1 1 in the diagonals thing. Is it? This is 1 1, and second last thing as determinant of A inverse, and the rest of the entries are 1 1 1. Okay. In the, so this is the thing 0 0 and AF 0 0 BF. Okay. So observe that. So A0 0 B, this going to determinant of A, AF, BF is a homeomorphism. This S of
Muna, I
UP,
didn't understand this part. How did you bring this determinant A inverse?
because since A0 0 B belongs to S of UP cross UQ, that precisely implies that determinant of A into determinant of B is equal to 1. That is a part of definition.
Okay, okay.
Did
fine.
you get it?
Yeah.
So that from there, from this is UP cross UQ to onto S1 cross SUP cross SUP. Okay, so this is an homeomorphism. So what I'm getting, so let us write this in space. So I am getting this S of UP. So this implies UQ. This is really S1, a homeomorphic to SUP cross SUP. Okay. So and this is really this whole thing is connected. So this implies S of UP plus UQ is connected, and this will imply that SU P comma Q is connected, and pi 1 of S of UP plus pi 1 of Z pi 1 of S. So this finishes about the pseudo so-called unitary group. Just I have to write one theorem, this is the same analogous theorem for this symmetric binomial algorithm. Let H be a non-degenerate.
So here it is semi-direct product or direct product?
Here it will be direct product. This is
Direct product.
because that is how this topology fundamental group we get.
No, not that. You only write the space. You just slightly go back to the previous page. Yes.
Actually, I didn't. I never thought probably it will be a product or semi-direct product or something, but
No,
I
just
didn't want that.
No, just go back there. Just yeah. So how are you writing that? Again, you are using that expression, right? Determinant A 1 1
Yeah,
1.
actually, I am not bothered about this. Whether how is the group structure is, it is direct product or semi-direct product. Only I am
The
bothered about
topology is product topology. That is clear.
that is clear.
You are not
Actually,
saying it's a group homomorphism. You are saying it's
yes,
a homeomorphism.
homeomorphism. Actually, this thing, previous thing, actually, I could have avoided it, but I thought that it will be good for to know something actually. Okay. So that is the reason that actually I could have avoided directly. So
Okay.
let H be a non-degenerate formation form of signature P comma Q on a actually analogous to the bilinear case. You define signature P comma Q signature in this case also dimension P plus Q. So then there exists ordered basis S is equal to V1, V2, Vp and Vp plus Q, such that H of Pi Vj is equal to 0 if I not equal to j, and H of Vi is equal to 1 if 1 less than equal to I less than equal to P. So now H of Vi is equal to -1 if P plus 1 plus Q, and proof actually similar are well, I could not locate a proof of this result, but I could do it this result by just using idea of Eilenberg form. So I will write that. So I use ideas, similar idea. To that of symmetric binomial. So you can look at Huffman-Kunze and write a proof on your own. So now it has two obvious corollaries, and remark. So there is precisely one non-degenerate formation for signature P, Q exist on a complex of a dimension P plus Q of two equivalence. So second remark, if S, B, H, so it's okay, B, you're right. If S, B, H are as in the previous theorem, the associated matrix of H with respect to the basis S is IP, Q, and ought SH is your QP. So this is the corollary remark, important remark. So now this finishes the thing about this Hermitian form. We will now take up something. Okay, we will come back to our first lecture first. So, and we will do something, and then we will pick up something called symplectic group. Okay, so recall. In the past lecture, we have considered this vector space Cn as a real vector space, and also we have identified as a real vector space with R2n. Okay, so, and what is the identification? This x plus iy, this maps with xy, and also here there was a multiplication by I. And it was really the corresponding, there is a corresponding map on R2n, and that map was nothing but j of xy is equal to minus of yx. Okay, so using this, I really say that MNC is equal to, okay, so this is really T belongs to M2 and R. Okay, so that Tj is equal to Jt. We have seen this, and also we have seen that GL and C. So T belongs to GL2 and R. So that Tj is equal to Jt. Okay, so look at the first thing. MNC is equal to T belongs to M2 and R. So that Tj is equal to Jt. That means T is a complex linear map on Cn if and only if T is a real linear map on R2n, and it satisfies Tj is equal to Jt. But what is this condition? That is only this condition. T respects the multiplication by I. Multiplication by I. Okay, this much I have shown. So T belongs to MNC if his TL is T is a real linear map on R2n, and T respects multiplication by I. This much we have seen. So we have, by this we will get an embedding of MNC inside something like M2 and R. Okay, we call this vector Z. Okay, and Z of A plus IB was nothing but This is A minus B, BA, okay, and A B belongs to MNR. Okay, let us okay, so let U belongs to MNC, and U is A plus IB. Okay. This A is called real part of U, and B is called imaginary part of U, for obvious reason. So now in this, now we can really write that so Z of U is equal to real part of U minus imaginary part of U. Okay, imaginary part of U and real part of U. Okay. Now we will investigate the properties of Z. So now properties of this map Z. So first property is very clear. So Z of U1 plus U2, this is equal to Z of U1 plus Z of U2. Okay. Now this is, you call this first property A. Okay. So now this, because this is, if U1 real part will add with real part and imaginary part will add with imaginary part. So this first property is very clear. U1 belongs to U2. So Z is equal to Z of alpha U is equal to alpha of ZU. Alpha is a real number. So then it will, this is also clear, because a real part of alpha U simply alpha real part of U, and imaginary part of alpha U is alpha into imaginary part of U. This is also clear. So this this first part, property 1 and 2, A, B, this will say that, so A comma B say that Z is R linear. Okay, but Z is R linear between two vector spaces, MNC and M2 and R. So, and these are finite dimension vector spaces, and therefore it is continuous, and thus Z is continuous. This is clear. Now second shares third property is also clear. Z of U1 U2 is equal to Z of U1 and Z of U2. You simply say that Z really well behaves, Z is well behaved with a composition. Okay, and this is actually immediate to me the way it is defined. If you are not unable to see it now, you do it an exercise, you take it an exercise. So one possible way to you let take U1 is equal to A plus IB, U2 is equal to some A prime plus IB prime. You know the expression of ZU1, ZU2, and multiply, you verify it. This is a simple computation, but my suggestion will be just do it without using the calculation. Okay, but this C property is very important. So D Z of e to the power U is equal to e to the power ZU. Okay, this will follow if you use A, B, C. So for that reason, this use A, comma B, comma C, and continuity of Z. This D is also clear. E is Z of U star. Okay, this is called to ZU star. Okay, so take it in an exercise. Okay. Now ZU is a real matrix, right? By definition. So this will be, sorry, this will be same thing as ZU transpose, because ZU is as real, as ZU belongs to M to NR. Okay. Now you look at this matrix. Okay, so if I will take trace of ZU, so I will get what? 2 trace of real part of U. Okay. This will be also important in later, this relation. So I will make that a property F. Okay. So trace of ZU 2 into trace of real part of U. Similar last property is very non-trivial and important. So I look at determinant of ZU. So this is actually ZU is a real matrix. So this you will get the determinant of U mod square. So last property is I will prove. Okay, so before proving that, I just want to mention a fact from linear algebra. So fact. Okay, so let Wx y comma z belongs to MNR and Wx comma y comma z. Oh, not really. Yeah, so say P. Yeah, so let us see A comma B comma C comma D belongs to MNR and A comma C comma D commute with each other. Then determinant of A, B, C, D. This is the block matrix and this is a 2n cross 2n matrix. So this is determinant of AD minus BC. So this is a very simple useful fact from linear algebra. We will use this. Okay. Okay. Now suppose now I want to give the proof of G. So what was G? G was this statement. So let us write determinant of ZU is equal to determinant of U square. This is my statement. Okay, this I want to prove. Okay, first let us say suppose U belongs to MNR. Okay, so what is ZU? ZU is equal to U0 U because imaginary part of U is 0. So then this is implies determinant of ZU. This is determinant of U square and U is a real matrix. This is the same thing as mod determinant of U square. So in this case, we are done. So in this case, we are done. Okay. Now I have told you that so GLNC is nothing but T belongs to GL to an R, T, so that T is equal to JT. This in particular will imply this thing that actually in the past class itself we have discussed this. Use invertible if and only if ZU is invertible. Or so this is easy to see and you can argue this in various examples, various ways. Now for instance, this GLNC is equal to GL2NR, so that T is equal to GLNC is equal to T belongs to GL2NR. So that Tj is equal to Zt. From there, you get this U is invertible if and only if Z is invertible. So this implies determinant of U is equal to 0 if and only if determinant of Z is equal to 0. Okay. So in this case, this relation is also holds trivial. So if hence if U is okay, determinant of U is 0, we are done. So it is true. So assume that U belongs to MMC and U is invertible. So you know that any invertible matrix you can really write in the products of elementary matrix. So let U is equal to U1, U2, Ek, where this Ei is our elementary matrix. Okay. Now this is, so that means okay, now as this is the thing, Z of you know that as this Z of U1 U2 is equal to Z of U1 into Z of U2, and determinant map is multiplicative. It suffices to show it for elementary matrix. Because because determinant map is also multiplicative. Is it clear, Pushtida? As I think he is not here. I don't know. Monosda, is it clear?
Yes, clear.
Yeah. It suffices to show it for elementary matrices. Now, what are types of elementary matrices? So first type of elementary matrices, you know that interchange of two rows. So second thing is addition of two rows. Third thing is multiplication by a row, multiplication of a row, of a given row by non-zero complex scalar lambda matrix. Okay. So observe that interchange of two rows, first one, and if you take the elementary matrix of type 1 and type 2, these are actually real matrices. So operations in since operations of operation of type 1 and type 2 corresponds to real matrices. In this case also we are done. So we are left only in the type 3 case. Okay. So let E be the elementary matrix which multiplies the kth row by Z. So let E be the, and what will be the E? This E will be the diagonal of, this is 1 1 1, and this will be Z. This is equal to 1 1 1. So, okay. And Z will be in the kth place, right? And determinant of E is will be Z. So this is by default. Now I will write this is diagonal of 1 1 1. Okay, so I will write this Z is equal to x plus iy. This is equal to 1 1 1. This is really in the kth place. So I will write that in a plus ib form. So first will be diagonal of 1 1 1 x 1 1 1, and second thing is this will be diagonal of 0 0 0 y 0 0. So this is in the kth place. So this is y is in the kth place. This is, you remember this thing. So that, okay, I should put I somewhere. Okay, sorry, plus I into, this is plus I. So I really, first thing actually, I call this A and call this B. So A plus IB, and A by A I mean this is my A, and okay, so this is my second thing is my, this is my B. What is happening? This is my B, okay. And A and B will commute with each other. So, but because these are diagonal matrices, so AB is equal to B. Now, what will be ZE? ZE is equal to simply A minus B, BA. Now, I will use that fact that if A, B, C, D commutes with each other, then determinant of, so but by that fact, so determinant of ZE will be determinant of A square plus B square, right? By using the linear algebra fact. So now, so determinant of ZE. So what will be A square? This will be determinant of diagonal of 1 1 1. If you will square it, this will be x square. This is 1 1 1. This is the, this will be in the kth place, plus diagonal of 0 0 0 0 y square and 0 0 0. So that will be determinant of diagonal of 1 1 1 x square plus y square. This is equal to 1 1 1 everywhere. So that will simply, this is x square plus y square, then this will be mod z square, and mod z is equal to nothing but a determinant of e square. So this finishes the proof for type 3. So this finishes the proof for So is this clear, Ushchap Devan? Or is this proof is clear?
Yes, it's clear.
Okay, so now okay, so these properties actually we'll need in future. So just you now we will really again little bit come back to this thing, and you know that this the CN we are identifying this with R2N, and this is my map. Okay, x plus IY, this you are mapping with XY. Okay, this is my map. So trivially, it is really x plus IY norm on CN, the same thing as XY norm on R2N. Okay, this is clear. Now you take you have the embedding this ZMNC to this M to NR. This is my embedding. So you take U belongs to MNC and ZU belongs to MN to NR. Now you will act on X plus IY. Okay, and ZU will act on R2N. ZU will act on X, comma Y. Okay. Now I just want to see what is the relation between. We have done this, but I just want to recall what is the relation between U of X plus IY and ZU of X comma Y. Okay. So so one thing actually you should remember always in your mind. Here actually I have written X comma Y in the form of a row vector. Okay? But when you really do the operation, then when you multiply, and ZU is a matrix, when you really look for the exact operation, then what you do, you really write ZU and you write X, Y in the column form, and you multiply into how the operation should be. But writing row, uh, actually we do not write in column form because writing will be cumbersome. And but when you write in the terms of row form, then you understand that what I am doing. Okay, so now suppose this, so let U of X plus IY is equal to U plus IB. Okay, so this is really, if you have followed my past lecture, then this is same thing as ZU applied on XY is U. If you have followed my past lecture. Pritam, is this clear? Pritam? Yeah, what did you say? Just repeat it again. U of X plus IY is equal to U plus IB. This implies Z of U of X, if and only if ZU of XY is equal to UB. Okay, so let me explain that. Because you know that A plus, how I did it. So, okay, so let us write here. How I did it, I let U is equal to A plus IB, U of X plus IY, this is A plus IB into X plus IY, right? This is like AX minus BY plus I into, this is AX minus BY plus I into AY plus BX. And if you you take ZU XY, this is nothing but A minus B okay, so for that reason, you look, if you call this as U, This is call this as UV. Okay, so this is actually U plus IV. Okay, so that's what I am writing. U of x plus IY is equal to U plus IV if and only if ZU applied on XY is equal to UV. So this is clear, I guess. Pritam, now it is clear.
Yes, yes.
Pritam? Yes.
Yes.
So, okay, so this is the thing you have to. Okay, so okay, good. So now let x plus I look at this inner product x plus I plus x plus x I prime y prime. So this is same thing as x y dot x prime plus I y prime. So bar this is x plus I y dot x prime minus I y prime. This is really x prime plus 2y dot y prime minus I x dot y prime minus y dot x prime. Okay, so this was the inner product on Cn. I will take this. This is xy x prime y prime on R2n and minus I. Our second thing is I will write wxy. Okay, wxy and x prime y prime. Okay, so now you recall if you take this w xy and x prime y prime, this is nothing but x dot y prime minus y dot x prime. If you recall the group sp2nr, this is actually the bilinear form for the group sp2nr. sp2nr. If you really recall this thing, and this is called w is called symplectic form. Symplectic form, but we will come back to this group later. But this is the thing you should really remember. Now, okay, so let okay, so okay, so really let us take this as star. Okay, so now I told you let u of x plus iy is equal to say u plus iv. So that is equivalent saying that ZU applied on xy is equal to uv. And similarly, u of so let u of x okay, x prime plus iy prime is equal to say u prime plus iv prime. That is equivalent to saying that ZU x prime y prime so now I look at this ux plus iy ux prime plus iy prime on Cn. So this is equal to u plus iv. This is equal to u prime plus iv prime on Cn. But I will use this relation star. Okay, so if I will use this star, okay, so I will get here. This is u v is u prime v prime on R2n minus I w u v u prime v prime. Okay. Now I use this fact that ZUXY, this thing I will use. So this will be equal to ZUXY. Okay. So ZUXY x prime y prime on R2n minus I w ZU. I will take 5 minutes more just to complete something so that we can start a new new group tomorrow next class. So this is a very important relation. Okay, so let us call this say 1. Okay, let us write this in different things. So u of x plus iy and u of x prime plus iy prime Cn, this will be zu xy zu iw. Okay, so that is the thing. Oh, sorry, I should put here a bracket. So this is you call this as relation 1. Okay, so now if x plus iy is equal to say x prime iy prime, then this will imply that xy is equal to x prime y prime. So now if I put that, then second thing is actually a w is a this is actually antisymmetric bilinear form. Antisymmetric bilinear form. So if I will put that, so you will get that u of x plus iy in norm Cn is equal to zu xy norm on R2n. So this is the second important relation you will use. And third thing, actually, I have already told that x plus iy norm on Cn is equal to xy norm on R2n. Now, second important proposition, just I will take 5 minutes more just to finish this thing. So, proposition. So, first proposition, un is equal to GLNC intersection O to N is equal to GLNC intersection SO to N. So you will see that this proposition itself doesn't make any sense, because UN is an cross N matrix and GLNC is an cross matrix and O2N is a 2N cross 2N matrix. But we can give a meaning to it, and the meaning of that is something like Z of UN is equal to Z of GLNC intersection O2N. Okay, so Z is the map which embeds Mn to M to NC, M to NR. So this is called Z of GLNC intersection SO2N. We will prove many results of this type, and this is the first result of this in this reaction. So I will do it very carefully. Okay. So what I will prove? I will give the proof of A prime. A prime. So let okay. So A prime is this thing. Let T belongs to ZUN. Okay. So by definition, this is really ZUN is contained inside Z of GLNC by definition. Now, as T belongs to ZUN, so this implies T is equal to some ZU or some U belongs to UN. Okay. Now, as U is an unitary matrix, we will preserve norm on Cn. Okay. Now we have seen that this thing is equal to really ZU applied on XY, and this is norm on R2n, and similarly this thing I have shown that this is really XY norm R2n. So this is equal to this. So ZU preserves norm on R2n. So that implies ZU belongs to where? O2n. This is clear. Now T is equal to, and what was your ZU? This is was equal to T. So T is equal to Z O2n. So you have started with, so this call this is 1, call this in 2. So this implies from 1 to N2 and 2 we get T belongs to where Z of GLNC intersection O2n. This is clear. Conversely, okay. Conversely, let T belongs to where Z of GLNC intersection O2n. Z of GLNC intersection O2n. Now, so from T belongs to GLNC. So that implies, so I will use the first thing first. So this is that T is equal to ZU for some U belongs to GLNC. Now as T belongs to O2n, T applied on XY norm on R2n is equal to XY norm. T will preserve the norm on R2n. So this T is, you can write that T is equal to ZU XY norm on R2n. Okay, this is. Now you really use that fact that ZUXY is equal to U. This CN. So use this relation. This is, I think you have seen that. This implies U belongs to UN. This implies T is equal to ZU belongs to ZUN. So you have started something like T belongs to Z GLNC intersection O2n, and you have shown that T belongs to ZUN. Hence the proof of A prime. Hence the proof of A prime. So I have finished the proof of A prime. Now B prime for B prime. So you have, so since this GLNC is connected and Z is continuous. So Z of GLNC is connected. So that means so Z of GLNC will lie inside something like GL plus 2NR because it is connected. Okay, so it would lie inside a connected component. So Z of GLNC will lie inside GL plus 2NR. So the thing is, okay, so from there, actually you will get that Z of GLNC. Okay, from here you will get that Z of GLNC intersection O2N. Okay, the same thing as Z of GLNC intersection SO2N, because now you have proved in the first thing that this is equal to Z of UN. So we wanted to prove this thing. So this finishes the proof of B prime. Okay. And Z of GLNC is contained inside GL plus 2NR. You can also prove that from this thing from G. Z of GLNC is contained inside GL plus 2NR. You can prove from G also. So this actually really finishes the proof of B prime, and with this I will stop. And from the next class we will talk about quaternion and then symplectic proofs. Okay, is there any question? Oh, sorry, I took almost 15 minutes extra. Are there any